il prossimo talk Sebastián ci illustrerà praticamente Windows Read Hijacking, Maintaining Access on Windows Machine, perciò dalla Privilege Escalation adesso siamo alla persistenza, che è una fase successiva chiaramente di un attacco. E Sebastián ha presentato già questo talk al Black Hat, perciò è un talk interessante sicuramente, è una tecnica che ha scoperto lui e che... per favore silenzio, grazie. È una tecnica che ha scoperto lui e che è molto pericolosa e che consente, come dicevo, di fare persistenza. Passo la parola a Sebastián. Parla in inglese.
Hello, I am Sebastián Castro. I am from Bogotá, Colombia. Today I'll be sharing with you a research I have made on Windows persistence. As Giovanni said, I have presented this also on Black Hat this year. I have named it ROD Hijacking, Maintaining Access on Windows Machines. I would like to thank to Giovanni and all of the staff from ROMHACK for letting me share with you this research. So this is about me. This is also my Twitter, Roder. I am an info security nerd. I like exploit development, and I am a Windows security enthusiast. I am not an expert. And I am the current technical research lead at CSL Labs, which is a Colombian company that works mainly on providing pen testing services, mainly to financial companies. I have been working on the field since 2003, and I got interested in the Windows security since I have started. So, this will be the agenda of this talk. First of all, I will expose the attack, what is properly the ROD hijacking, and a quick overview of how does it look like when it's executed. Right after, to properly understand the attack, I will explain shortly the Windows security architecture and the security task related to the hook. Here in Hijacking the RID, I will point out where exactly the security issues are found that make this attack possible. And to demonstrate the effectiveness of this attack, I will do a live demonstration with a Windows 10 virtual machine I have updated last night. And we'll test the RID hijacking attack with a model of Metasploit I have developed to automatize it. After that, some final conclusions. Of course, I'll be glad to answer all your questions at the end of the talk. So let's meet up the RID hijacking attack. What is the RID hijacking attack? It is a new post-exploitation vector which is reliable on all Windows OS versions since NT. I have tested it from Windows XP to Windows 10 and Windows Server 2003 to 2012. Haven't tested it on Windows 95. If you can test it and if it works, let me know, please. It will create and stealthy access on the target, all by using OS resources, which means that no noisy extra files are needed that could trigger any alert on the victim. Properly, this attack takes advantage of some integrity issues I have found on Windows Security, and it is reliable on domain member workstations and server, not currently on domain controllers. I am working on a similar attack which is reliable on domain controllers. So, in short, this attack will hijack or assign the relative identifier of an existing account and will set it up to another one. Just the RID, meaning that all the other account properties, such as the username, such as the password hash, the account status, will remain the same before and after the attack. By hijacking the RID, also the privileges are spoofed. But one interesting thing, is that no matter the hijacked account status, active or no, the hijacker account will be capable of retrieve the privileges of the spoofed account as own. So remembering that only the RID attribute is modified, an attacker could log on with a specific credentials he owns and will grab the privileges of another account. And on most configurations, I have seen mainly on domain members, on domain joined machines, sorry, a remote access is permitted. So you can access by using this attack by using remote desktop, PSXec, and it will be possible to authenticate with the own credentials remotely in most configurations. And after a successful logon to the victim with these credentials, the system will register any operation which has taken place during the hijacker session and will register as done by the spoofed account. So this is how it looks like. So in this image, we are authenticated. Let me see. Yeah. We can see that we are authenticated as the guest user. If we query our privileges by using the net user tool, we can see that we are only members of the local group guests, but we are capable of writing on protected folders. In this case, we are writing on System32 folder, which is cool. So, to understand the magic behind this, I will briefly explain how the logon process works. I forgot to say something about me, and is that I am terrible at Paint. Okay? So, I told you I'm terrible. Well, I think that the Windows authentication and authorization architecture is similar to the security concept of some buildings have been on. So you introduce yourself in front of the person in charge. The person in charge verifies if you are registered, and if you are, then he provides you an access card, which permits you to get into the zone you are allowed to. This is the access token that Andrea have mentioned in the last talk. So, for understanding our purposes, this will be our character. So this will be the administrator account. This will be our main character, which will be an unprivileged account. Unprivileged account, in this case, is the guest one. The bad blue guy will represent the Windows security. And this ugly building, the Windows operative system we are attacking. So inside this building, imagine that there is an RFID-alike control system managed also by this blue guy. So to keep it simple, I have drawn 3 floors to represent the privileges an account can get. As we have seen, there are a lot of privileges, but it's hard to draw them all. So depending on configuration, guest users can access or only can access to the first floor. Standard accounts will acquire the privileges of the first floor and the second floor, and administrator one will get everywhere inside the building. In a more technical way, when an interactive logon takes place on a Windows machine, many objects of the system get involved. But the most noticeable are WinLogon, the LSASS, which is all of this, the security hive, the SAM hive, and the, in this case, which is related to domain controllers, the ADDB, which is stored in the NTDSF. However, the RID hijacking attack is focused on local users' login attempts. So we will ignore by now the KDC and all the authentication packages related to Kerberos, and we'll be focused on the LSA server, the MSB1DLL, and the SAM server. Okay, in a nutshell, the logon task is this. I know that many of you have seen this graphic before. So we are here, authenticating as administrator account by using the administrator and password triangle. We authenticate by using WinLogon. And after that, if we have access to this machine, the WinLogon, the LSASS with a connection, an LELPC connection with the security reference monitor, will create an access token that will define the security context of the user session. The security reference monitor is a kernel mode process which is in charge of creating that, and also is in charge of checking the security context, or I mean the access token, with the file discretionary access control list to verify if a user has permission to access or not to an object. All of this is done by using security identifiers. So this is the structure of every security identifier that is used to represent all the security principles on a Windows system. So the first part in yellow is the one which differentiates of the machine or domain among others. But the last one, this one, is the relative identifier that can be the same across all machines. For example, in every Windows machine, you can find that the administrator building account will have the 500 relative identifier, the guest account will have the 501, etc. So remember that every user account, built-in or not, has its own RID. So suppose that the administrator wants to log on here. So he provides its username and password to WinLogon. To do that, Windows needs to initialize some tasks and connections between processes. And right after, WinLogon will call Logon UI to grab the credentials by using credential providers. That will define the way that Windows will process the entered credentials. After that, with this information, WinLogon will create a unique identifier to differentiate this logon attempt. And WinLogon will call LSASS, retrieve a handle for an authentication package. But what is an authentication package? As I have told you, there are two that are the most common are the MSB10 and the Kerberos one. These are DLLs that verify the authentication policies, such as matching user passwords, verifying some account restrictions. But for the RD hijacking attack, we will be focused on the MSB11. So, continue with the authentication process. WinLogon will send the authentication package with the combination of username and password and the recent created identifier for this logon. And then this critical step, the MSB1 will send the username password combination to the SAM server DLL. And right after, the SAM server will query up the SAM registry hive and will retrieve some important information associated with this account. And now, to sum it up, the MSB1 will check the information retrieved. If it is okay, it will generate an identifier, which is called LUID. And all this data will be used afterwards to create the access token. So, hello? Okay. Now that everything is, the Windows Security Subsystem proceeds to the authorization process to create the access token. Will define the security context of this user. So the access token is used to define the security context of a process and also of a user session. This object, as I've told you, is created by security reference monitor. And it's important to notice that every child process will inherit a token copy of their created one. So, meaning that every process within a user session will be with the same access token. Well, right after the initial access token, the LSASS will receive the logon information from the SB1, and will check it up its own database with which is the security registry hub, to determine the user's allowed access. This check is done by using the security identifier that has been added here. And right after, the LSASS will add all the privileges associated with this security identifier that differentiates this user. And finally, it will create the primary access token that will define the security context. So in this case, we can see that administrator has received his own access token, and it will be allowed to move everywhere inside the system. So now that we went through the standard user logon process, let's take a look at the things we're interested in. So where in the process are something exploitable? So here's a quick question. How is the user identified by the system after being successfully authenticated? Yes, it's identified by its ID, which is unique in this host. How does the system associate a user with his security identifier? Using black magic. So let's see that. So remember this part of the process. Here is the exact moment that username is translated into his associated security identifier. So right after doing this translation, some important security information is retrieved from the SAM. So it's properly the username associated with this security identifier, and what security information is retrieved from the SAM. The SAM server is in charge of querying up this registry hive and will translate from username to password with these steps. So he goes into the SAM database on this registry key and will select the specified username. We can see it here. Right after, it will enter inside the key, and each of these registry hives will contain a ref binary inside of them that have an attribute called type, and this attribute contains the hexadecimal version of the relative identifier of the user. In this, the relative identifier is 3E9, which in decimal base is 1001. And now that the SAM server knows which ROP is associated with this username, we will query another registry hive, which is this one. And we'll choose the one whose name is the same relative identifier stored in the rec binary we have seen before. Then it will grab all the information stored into the reference key. And it will send it back to the authentication package MSB10. And after some questions may arise after understanding this process. So why does the SAM only store the relative identifier? In every machine, every user will have the same first part of the security identifier, and the last one will be the one that will be changing inside that system. So what information is received from the SAM? Data obtained from the registry will contain the password hash, which is encrypted with the system boot key, will contain the account status, active or no. It will contain some additional account restrictions, but it will contain something interesting, which is a copy of the user's relative identifier inside this binary. So let's exemplify the attack. So let's try to do the authentication process with this red girl, and we will meet some parts of the authentication process, and we will be focused on the interesting one. So a meeting in the beginning related to the authentication and WinLogon stuff. Let's assume that WinLogon has done everything well and sent the login information to the MSB1, and after that, the package MSB1 will send a combination of the username and the password to the SAM server. Now the SAM server will query the SAM database looking for the associated guest key. Then it will retrieve the hexadecimal version of the relative identifier, in this case it's 1F5. SAM server will query again based on this recently acquired information, this specific registry hack, and the process will retrieve the security data related to the user, including this RID copy, which is stored in one of these binaries. And after that, SAM server will send this back, this information back to the MSB1 authentication package, and this guy will do his job. So this could lead to two possible scenarios. The first one is that the hacker guild, which is representing the guest account, will not authenticate because on every Windows machine, by default, the guest account is disabled. So we are going to get an access denied. On the second scenario, supposing that for some reason the guest account can authenticate against this machine, she will receive her access token, and then well, she doesn't get kicked off, but has access only to this first floor. So how could we improve this situation? So what would happen if the RID copy changes to another value? So this is the core of the RID hijacking. I have found that this particular value, which is stored in a specific binary inside Hive, is used by the security reference monitor to create the primary access token, which means that if that value is modified to another one, it will assume that this is the correct value associated with the user when creating the primary access token. So we are changing from 1F5 to 1F4, and we are switching the relative identifier from the guest one to the administrator. So repeating all the process, MSB1 will send a user hash to SAM server. SAM server will query up the SAM with the guest username. It will retrieve this registry Hive, this rec binary, and will obtain the relative identifier 1F5. Right after that, it will query again this 1F5 registry, and now it will receive the security data from the SAM, including this modified RID copy. This data is sent back to the MSB authentication package, and now the MSB1 package will check for restrictions for this user, obtained from the SAM as for the SAM as security data. The thing is that MSB1 will take the status of the guest account, which is active in this case, but will assume that it is the administrator one. So it will be possible to authenticate with privileges of the administrator. So when the MSB1 does the authentication verifications, it will seem that the hash password entered right at the beginning of the authentication process will be the same as one which is stored into the sum. So now that everything is okay, the authentication package will retrieve the information to the LSASS, and then, with the help of the security reference monitor, it will create the primary access token. All security properties of this account will remain the same, but the RID, the critical one. So getting the RID, in this case, is equal to acquiring the privileges of the spoofed account. So, and doing everything, you can do everything you want with this new privileges acquired. In this case, this red girl is authenticating with its own credentials, but she is getting the privileges of the administrator one, so she can do anything inside the system. Only half the administrator account. So these are the proper security issues that allow this attack being possible. So the first of all is that some server does not check if the relative identifier associated with consistent with the RID copy, which is stored in the binary, is used by the security reference monitor to create access token. LSASS does not corroborate the RID with the username before creating the access token. And the LSASS never looks for RID inconsistencies during the user session after being authorized. So this will be the interesting part. So this is the architecture of the demonstration I am planning to do. So it's quite simple. We'll try to authenticate with the guest account and a privileged one, which is not different than standard user account. We'll try to authenticate against a Windows 10 machine. I have updated last night by using interactive logon, remote desktop, and PSXX. And we will do the RID hijacking attack with the Metasploit module I have developed by using this Kali Linux attacker. So, get into it. Yeah. Okay, so you can see here that, no, we cannot see that. Let me see. Okay, I got it. Yeah, now can we see? So this is the virtual machine we are attacking. We can see that this is the latest version. Actually, yeah, it's updated early this morning. We can see here the IP address. We are attacking this IP address. And this will be the attacker one. This is the model we are going to use. You can find it on the latest Metasploit official release. This is the attacker IP address. Okay. Nothing. So let's try to authenticate with the implemented version of PSXX against this. Okay, it's not possible. I have enabled the guest account in this case, but we get a type not granted. Okay, logon type not granted. And let's see here. These are the users that are available on these machines. Trader built-in account. Here is guest account. And here is one standard user account we are going to use to exemplify the RD hijacking tool. So if we query up the user guest, we can see it is only a member of the local group guests. Nothing different. It's enabled. The account is enabled. Net user administrator. This account is the built-in one, and it is disabled. We can see it here. All right. So, since this is a post-exploitation technique, it requires a meta-interpreter session to properly automatize this attack by using the Metasploit module I have developed. But this executed resources. So let's see the session of interpreter. These are the session, okay. And let's see the options. These are the options of the module. These are the guest system. We'll try to acquire the recorded privileges to automatize the stack. This will be the Boolean that will define if we are going to use the guest account as an attacker one. The password, if we want to change the guest account password. The relative identifier we are planning to set, and the session of Meterpreter. So in this case, we'll try to set these values. We are going to use the guest account, and let's set a password. And set session. Okay. So right before doing something, I will try to interactive logon by using the guest credentials, so we can see it more clearly. Okay, it is not possible for us to authenticate even in this interactive logon by now. And let's execute the already hijacking attack. These are our values, and let's write exploit. Okay. Now we have changed it from RID 501 to RID 500. So let's try again to authenticate with the guest account. Okay, it seems that we are capable of authenticating. Nothing impressive by now, but if we try to do the PSX version of InPacket, here. Okay, it will be possible for us to get a shell, a system, by using the guest credentials. So it is possible also to do an interactive logon. So in this case, we can see that we are guest. But the interesting thing here is like we have the relative identifier of the administrator. Okay. It is possible for us to do some interesting things like creating some interesting file like okay. Pretty cool. And the thing is that If we query up our privileges here, let me see. If we do something like a net, let's do it here, net user guest. We are only members of the guest group, so if an administrator will check our privileges there, we are only guests, but we are capable of things as administrator. And if we take a look on the administrator, sorry, user, you will see that this account is disabled. So we are doing things as a disabled user. We are spoofing the privileges, all by doing this attack. But someone will say, no, but this only works with the guest account. No, that's interesting because this is reliable for every standard local user account. So if we try to use, let's query the unprivileged account. Let's query it here. No, that's this one. Net user unprivileged. Okay. We see that we are only membership. We are only users local group, which is a standard user account. If we try to do a PSExec of the, remember that the in-packet version of PSExec will try to acquire system privileges if possible. So if we do that, privileged. Okay, no, it didn't work as well. See that. No, it's really weird. I think that I have already hijacked the unprivileged account, but but let me see, the user unprivileged. Yeah, I think that I have already hijacked it. You can see that we are only members of the user group of this group, but we are capable of deploying a system session with these credentials associated with the unprivileged account. Okay. So, there are some final conclusions. By now, as you have seen, there are no existing patches provided by Windows to protect their system from this attack. The only way I think a machine is by detection by now. Of course, there are solutions that are related to modify and properly those that are related with the authentication and authorization process. Okay. Sorry about that. Yeah, it is working? It's not working properly? Oh, okay.
Okay. So check.
Yeah, sure. Yeah.
Sorry.
Okay. Better? Yeah? Can you hear me? Okay. So, as I told you, by now, the only way to defend from this attack is by detection. You can verify if this RID copy is consistent with the one which is associated for this user. There are some workarounds to detect this, like developing some scripts which hide privileges to check the SAM registry hive and compare the value which is stored inside the rec binary with the RID value which is assigned to this user. Of course, this kind of detection is more complicated on big Windows domains, since a simple workstation can have this and it can be used to an entry point for an attacker. So I have worked on some workarounds. I'm trying to automatize the way to verify if the relative identifier
associated with the user is consistent with the one which is stored inside of this binary. Okay. So I think that's it. Thank you so much, and I hope you like it.
Grazie a Sebastián.